Hello, everybody. I hope you can hear me well.
Yes.
Welcome to the Instrument Science session of the 11th ET Symposium. As you can see on your screen, the agenda today is pretty much dense. There are a lot of very interesting talks. It's 2:30 sharp. So my proposal is to start the session right away. Today we'll listen to several talks about the various divisions of the Instrument Science Board of the ET collaboration. You already heard a general presentation about the Instrument Science Board on Monday, and today my friend and colleague Andreas will just give a short summary of that general overview. So if Andreas is ready, the floor is yours. You can go ahead.
Yeah, I'm ready. Thank you, Gianluca. Okay, I hope you can see this full screen. Okay.
Yes.
On Monday, I've already given you some introduction to the ET instrument science, and the instrument science activities will be done within the scope of the Instrument Science Board, of which Gianluca and I are the chairs. And in this talk, I would like to give you a little bit of an overview of what this board is, because if you're interested in instrument science and want to contribute to ET, that's the place you want to be. So let me just show you a few of these organigrams to explain a little bit what we are and where we are. So this is a graphic of work in progress. We are at the moment, establishing a new structure for an ET collaboration and also the collaboration itself. And you see more about that part Thursday morning at 9 a.m., where we get an overview of where we are with that process. Now, what you see here was a snapshot of that I did some time ago, where you see dashed boxes. These boxes are something that I will not talk about because they are outside of the ISB scope or not yet implemented, but it gives you a bit of the context. So we have these kind of boards for different types of activities, and then we have on top of these additional management structures like the executive board. At the moment, we have a steering committee and so on. However, we did already implement one thing, which is the Instrument Science Board. It's kind of the driver of this activity. We wanted to start that first. So we started working on this particular structure. So also in here, so that the acronym for Instrument Science Board ISB is what I will use in the following. Also in here, you see two boxes that are dashed and have not yet been implemented, but the structure of the rest has been discussed for a while. Before I go to that, let me just say what the Instrument Science Board is for. So we've written down a brief mandate and describe what we want to do. And I think we can summarize that in two key aspects. The first one is that we're charged with delivering a technical design for ET, and I'll tell you a bit more in a second. And the second is to coordinate the R&D activity that is needed for realizing ET, and here the R&D in particular for the detector, so for the instrument. And so that is not so different from, let's say, working groups in current projects, like LIGO and Virgo or Kaga. The difference is that we are not yet having a detector, so we are in a slightly different phase of the project. And that brings me back to the technical design report, which comes in a few phases. As you will remember from the introduction talk, we are at the moment preparing the case for the EU, have submitted an application to be on a roadmap. And one of the key milestones will be a site selection. And for the site selection, we have to make a cost evaluation and make a detailed studies of the site. But for the cost evaluation, you also need to know what you want to build. So our first task will be to have a preliminary design review ready for this process. But once you actually then have a site chosen, then you have to make a design for that particular implementation that you're going for, and then continue to the proper technical design. And I've written a few timelines here. These dates, 2022 and 2025, are estimated, and they are depending, of course, on some external boundary conditions that is not under our control, but this is what we're aiming for. So what I will show here is a little bit of an animation of the process as we were discussing this. You see, we had different ideas, and we're changing the larger boxes and the smaller boxes and arrange different topics. And then we arrive finally at the one that we have now. I wanted to show you that to show you how much work has been happening behind this structure. So this is not something we just copied and pasted from an existing structure, but we thought a lot about how to do that best. And I named this slide Preparing for a Large Team, because we really believe we have to encompass here a very large project and have to manage and attract people from many countries in different aspects. And you see here we have 6 vertical rows, which we call divisions. And in each division, we have these kind of blocks that are work packages. Some notes on this structure, because they look similar, but also a little bit different from what you're used to. And that comes from some of the challenges of ET. So we have a division which is called active noise mitigation, which is not existing in current structures. And that's because we believe in ET, the low frequency noise and its challenges are new, are different, and require a specific focus. Some other changes are due to the fact that we start not by building the instrumentation, but by writing a design. But of course, as the project progresses, we would like to morph that structure into a structure that can deliver the project and then operate it. So we thought about how to arrange the structure that allows first an efficient design writing and later to friction-free move into the next one. And just for the organizational part, so we have 2 co-chairs for the board, that is Gianluca and me, and we have 2 co-chairs for each of the divisions. And then the work packages are going to be led by also co-leads or co-chairs. And we are at the moment in the process of defining that aspect of the structure. So we expect to have names for the work package chairs as a preliminary suggestion to be approved by the ET steering committee in a week or 2. Yeah, and just to be a little bit proud of what we've done, even though while we're still establishing the structure, we already did some work. One of the deadlines that we had was the application that we submitted to the EU for the S3 roadmap. As part of the application, we had to provide documentation. Obviously, one was a 30-page summary on the science case and design, where the Instrument Science Board wrote half of this document, and we decided to update the conceptual design from 2011, and we wrote this new or compiled this new document, the ET design report of about 200 pages. So even while we're not yet having this structure officially approved, we already work well together. It was actually a lot of fun. It was great to be back together in an ET team after many years of doing that more as side projects. Okay, and yeah, the organigram again, but here with pictures, if you don't know us yet. So these are the people that are already officially in place and have the charge to organize these activities for ET. So these are the primary contact person if you want to get involved. Half of these people will give the talks in this session, so you will see more of them. As I said, we are very close to finalizing the structure, and we'll then start with the usual kind of working package meetings, division meetings, discuss work, have interactions. So now is the perfect time to join us and to collaborate as much as you can. Everybody is welcome to join, and there are no official ET memberships right now. Just get in touch. And even later, similarly to Cosmic Explorer, there's no problem in being in ET at the same time as in other collaborations. Okay, that's all I have. Thank you very much.
Thank you, Andreas. Thank you very much for this introduction, also for being perfectly in time. We have time for one short question, and let me also remind you that at the end of the session, we will have 50 minutes for open discussion. So if there is one short question, if not, we can proceed with the second talk, interferometer division. I think that Jerome, I see that Jerome is already ready to start. We see your slides. Please, Jerome, you can go ahead.
Okay, excellent. Thank you, Gianluca. So good afternoon, everyone. So for the first presentation of the afternoon about the different divisions, so I will present about the interferometer division. So this division has two co-chairs, so Stefan Hilde and myself. And as it has been presented quickly by Andreas, it has 6 different work packages. And I will come back in this presentation, in fact, one by one to see what it contains and what is the scope. And like also it has been said, in the following weeks, in fact, it will be assigned for each work package, one chair and one deputy. So two persons to be in charge. So the first work package is Observatory Design in Noise Budget. So if you have not heard about the name of Noise Budget, is in fact an exercise where you calculate all the different noise which could limit the sensitivity of your detector in a kind of analytical way, relatively fast. You sum them up, so the noise will depend, for example, on the coating properties, on the temperature of the interferometer, the wavelengths, the length of the arms, and then it gives you basically your sensitivity curve. And from there, you can derive some figure of merit regarding the science. So for this works package, the first task will be to develop and update all the theoretical budgets, all the theoretical noise in the noise budget. It will also be used as an interface to the science case. So you must be aware that we have, I would say, different science targets. And they have different also figure of merit and may focus on different frequency band. So for example, the neutron star post major will be more to high frequency. And if you go to higher masses of fusion of black hole, it's more lower frequency. So sometimes you are not always, I would say, try to focus on the same part. And it means you have to do also compromise. And that will be part of this work package to have the right, in one sense, figure of merit, which can optimize all the science we can do, and also find the sweet spot or the best parameter. Like here is some example of what we can optimize. It could be the temperature of the optics for the low frequency interferometer, filtering cavities in terms of loss, length, frequency crossover, and so on, laser power. And also because the code will be fast, we can try, we can scan some parameters and try also a different scenario in a relatively quick way. And the code has already started. In fact, the code has been there, of course, since 2010 and before. But right now, there is a new version rewritten in Python. In fact, and here you could find a link on the presentation. And I also take some example from the slide you could find there. So you have already seen a similar plot around this switch. So just to remind you that the Einstein telescope, which is the bottom sensitivity curve with horizontal axis, the frequency, is quite ambitious and aimed to have, like we say, a general factor of 10 in sensitivity, but also push toward the low frequency in a very significant way. And how we can achieve this in the first strategy is to have a longer arm. So we are talking about 10 kilometers longer arm cavities. And also to not have one interferometer, but as you can see, 3 interferometers entangled in the triangle shape in 3 detectors, and each detector is 2 interferometers. And one interferometer will be as low temperature and one at room temperature. So that's why you have it will use also 2 different chain of material for the main mirrors, and so also two wavelengths. And as a result, in fact, you will take the best of 2 interferometers. So one will focus on low power, low frequency. So that will be ET low frequency, and that's the kind of left part of the sensitivity curve. And one will take care of the high frequencies. That will be the room temperature, high power laser. And when you combine optimally, in fact, you have a much broader sensitivity range. So that's the strategy for ET, as you already know. If you go more in details about the noise budget, so here we start about the low frequency. I will not pass through all the curves, but just what is interesting to know is the set of parameters that we'll use, which are the main parameters described on the right. And in the bottom, in the bucket of the sensitivity curve, we are mainly limited by the quantum noise. So radiation pressure noise at low frequency, and shot noise in one sense towards the higher frequency. And just below it has also the coating thermal noise, that it has been much diminished thanks to the operating temperature of 10 Kelvin. It should be mentioned that for both interferometers, we'll use routinely a frequency-dependent squeezing. And here you can see the set of parameters which has been used. For the high frequencies, the picture is a little bit different in the sense, in that case, we are a little bit still limited by coating thermal noise, and and for the high frequency is the shot noise, so what we call here a quantum vacuum. And for the low frequency, it doesn't matter too much because it's covered by the other interferometer. It will be the suspension. So right now it's still a work in progress, basically to be certain that we are using the right models. And of course, after it's easy also if new noise, we can imagine some new noise to add them. But this one should already be given the envelope of the sensitivity curve. So the second and third work package had the optical layout sensing and control scheme. For one is for low frequency and one is dedicated to high frequency. So it has two main work. Is first to develop the optical layout of the core interferometer. So what will be the position of your optics, where it will be, and also what is the specification. So all the optics will be curved. What is the state of the surface? Do you need a wedge? And you need to have a 3D layout and be sure that you know where your laser beam is going, and it will help you, in fact, to place all the other elements. And in parallel of that, you need to find the scheme, basically, how to bring your interferometer to your operating point. That's why we call the latching. So that's typically is to maximize the circulating power in the cavity. So you will have a feedback loop to control different degree of freedom. And once you know how you can arrive to the right operating point, of course, you have to keep it. So that's why it's called the less sensing control, which is a longitudinal degree of freedom. Typically, you have one per cavity. And the alignment sensing control is a kind of rotation and tip and tilt of your mirrors. And you need to have proper error signal to be sure that they will be maintained, in fact, in the right position. So the two work package, in fact, we rely they will share a lot of tools and procedures. So it will be same strategy, of course, not exactly the same parameters, but all the, in one sense, simulation infrastructure will be common to both. However, you must be aware that it still has some differences, as the low frequency part, of course, we will emphasize on the low frequency, where in high frequency, it will manage very high power, so 3 megawatt in the arm, so it's more than 10 times what we have now in LIGO and Virgo, and you have some effect of radiation pressure, which can, in fact, impact all your control loops. So that's why they will have also their own, in one sense, specificity, and that's why they are separated into work package, even if a lot of the work will be common, and it will have, of course, interaction. Here you will know more. It has already presented last Monday by Andreas, but it will have more about the design of the recycling cavity. And this one, it has an important impact, in fact, on the cavern and the excavation itself, because where do you put your mirrors, in fact, to be able to disentangle the two interferometers and be sure they will not overlap about the tower and all the optics. And like I said, tomorrow afternoon, it will have a dedicated talk about the strategy to manage, for example, to have a smaller beam splitter and how you can position them. The first work package is about data acquisition and real-time control. So it's to set basically, as the name suggests, the control and the data acquisition, the choice of the...
minute, Jerome.
Okay, so I will accelerate a little bit. It will be faster for the remaining one. The choice of the timing and distributed network, and also compared to the first work package, which are purely, I would say, simulation, this one will have some hardware. So it will have to take that into account. And to be more specifically, it will have some choice to be made according to the experience that we have now. Also, it will have a lot of input from other work packages to know what is the data flow, what is, for example, the sample frequencies they need. And after all of that will be all the structure and how we can access the data, how we can store there. So it has a lot of questions to be answered, but fortunately we have a good basis of experience also in the prototype which are developed or in the future upgrade of Viago. This work package, it's about noise characterization. This one is rather new. We don't have it as such in LIGO, means not in this form in LIGO Viago, because right now we are at the start of a project. And the goal is to include, in fact, some strategy in each work package to be able, when the interferometer is running, to project properly the noise, to know where it is on my sensitivity, where it is limiting. And that's something we may have missed, in fact, in previous generation, because we are learning. So here is really transverse work package to review and be sure we have implemented the right strategy to after do the proper noise budget. So here you have an example of, on the left is the theoretical one, that's what you hope to have. And on the right, you have the real one, it's more complicated. And the question is, are you projecting all the noise or do you have some missing gap and some extra noise that you cannot explain? So we'll make sure that we try to avoid that. So the answer in 20 years. And the last one is what we call the calibration. So it's at the output of your detector, typically you will record some volt. And how do you go back to the amplitude of the gravitational wave signal, the dimensionless famous H? So you have to derive the calibration requirement from the science goal. Develop, as we saw, we have different interferometer, different detectors, recombination, extract the node stream. And it's not only a software work, but it has also some hardware calibrator in one sense. So you have to know how you will use it, where you will put it, or you will integrate. And if we say hardware, we also say cost estimate. So here is some the requirements that we have now, just in amplitude and phase about the signal. And here just an illustration of two ways which are currently used and will likely also be implemented for ET. So photon calibrator to push the mirror with light, and the Newtonian non-calibrator where you use a Newtonian attraction basically to induce a displacement of your mirror that you know in advance. That is my last slide. So as you got already the flavor means in the previous 3 days that we have right now we have a chance to design a new observatory. I would say it's not happen often in a career. It's a long road ahead, but we have already a good basis with from 1G and 2G. So we are confident we can manage and we can take the best of what we have learned so far. Most urgent work means urgent is relative, but it's about the tunnel configuration because it's in fact it is a cost, so we need to be certain to have a robust optical configuration. And like it has been said by Andreas just before, so everyone is welcome to contribute. There is plenty of tasks in the different VPs, even if you want to learn. And if you would like to participate, don't hesitate to sign in, and it will have a lot of nice opportunities. Let's finish.
Thank you very much, Jérôme. Very clear exposition. Really a long road ahead, but it's going to be very interesting. Michele, I see you raised your hand.
Yes, I have a comment or a request. So you show that, okay, we need to recompute the sensitivity curve and have a new evaluation because the sensitivity curve of predicted sensitivity curve of ET it's has been computed time ago. One of, one point that I found very interesting was an evaluation made a time ago by Stefan Hilde that was evaluating the limit of the infrastructure. Because we are stating that the ET is, first of all, a research infrastructure, and then is an observatory implemented in this research infrastructure. So it will be quite useful when we evaluate the sensitivity curve is to distinguish between something that is due by the infrastructure and then something that is due by the particular implementation. I understand that is arbitrary and difficult. What means infrastructure? Vacuum is infrastructure or not? If vacuum is ultimate limit and so on. But I suggest really to investigate this point because it will be useful when we try to say, okay, we lost all the future implementations. Let's see what means, what is the ultimate limit. For example, look into Cosmic Explorer. They are sometimes comparing Cosmic Explorer 2 to ET, but there is 1 decade between the two. So I think we need to evaluate what is the potential of evolution of ET with respect to the initial implementation.
Okay, message clear. I don't know if we'll propose ET plus already, but no, we can explore that given the constraint, I will say, of keeping 10 kilometers arms.
Any more comments or questions for Jérôme? Okay, if not, we can move. Thank you again, Jérôme. Next talk, next ISB division is suspension. I see Alessandro almost ready. So Alessandro, please, you can share your desktop.
Yes. So good afternoon to everyone. Let's put it this. Okay. So can you see the slides?
Yeah, very well.
So about suspensions, what I would like today to do is that give a bit of background information for all the newcomers or people who is not deep in the gravitational wave business. So I will also introduce a bit the terms and jargon. So, but I would like to start with these numbers. So what we are talking about when we talk about the vibration isolation systems for the optics of ET, we should consider numbers of this order. We are going to make 200 in vacuum vibration isolation systems that are needed for the core, recycling optics, input mode cleaners, optical benches, mirrors of the filter cavities, which if you do a bit of math, you ended up with making more than 5,000 brace springs, more than 1,000 suspension wires. You need more than 1,000 ultra low noise inertial sensors for the controls, same several thousand displacement sensors, and same numbers of actuators. So it's a big system, what we are going to make. So, oh, sorry. So, concerning the seismic isolation of test masses, so to meet the requirement of the Einstein telescope, we need to extend the detection band to the low frequency region starting from 3 Hertz. So we need to improve significantly the seismic attenuation chains that we are using now in the second generation detectors. While using the current detectors, we will learn a lot, and we learn that in most of the cases the improvements of the in-band sensitivity of the detectors pass also through the reduction of the RMS motion of the optics at low frequency. The RMS motion, which is dominated by the microseismic peaks, is the driver of scattered light noise, and it impacts the dynamic range of linear angular alignment loops, etc., etc. So So besides taking care of what's happening in the detection band, so above 3 Hz, we had to take great care of what's happening at lower frequency. So we are going to deploy a lot of local and global control strategies to mitigate these effects. About the global control parts, you will hear more from Jan and Connor later. So for the seismic isolation of test masses, what we are going to do is to build on the successful experience of the Virgo super attenuator. So just to introduce the terms for the people who are not deep in this field. So in the super attenuator, the attenuation chain is quite complex. We start from a base ring or at ground level, so to say. Then we have a seismic isolation platform, which consists of a long inverted pendulum for horizontal per-isolation. These platforms also include a long period of vertical filtering stage, so-called filter zero. And the platform is instrumented with seismic sensors and actuators for active damping of all translational modes of the suspension chain. From the seismic platform, we can do large dynamic range actuation and seismic attenuation from a few tens of millihertz up to 10 Hz, roughly. Then hanging from the seismic isolation platform, there is the so-called suspension chain. Is a cascade of passive pendulum stages with low natural frequency vertical spring system nested inside. And this chain is the one that is providing the in-band bulk seismic attenuation for the detector. At the end of the chain, so if you come back to the bottom, there is the so-called payload, which means the test mass and is static and dynamic positioning stage. One thing is that so the base ring, it also including a component of the seismic isolation platform that is used to control the tilt of the platform itself. So when we wrote the CDR back on 2011, so it was clear already, because it was demonstrated, that the super attenuator as built and as operated now from in advanced Virgo was already compliant to satisfy the requirements of the Einstein telescope high frequency interferometers in terms of in-band noise. And then based on that, doing some math, we found out that just extending the length of the isolation of the various isolation stages of the super attenuator, we could meet also the in-band noise requirement for the ET low frequency. So this was the original idea. Is still the baseline of the project. Then, if you consider what we learn in terms of the impact of the RMS motion at low frequency, it's clear that we had to improve on this side. So not just taking care of what's happening in the band of the detector. So we did some exercise. There is some work being done at the moment in this time. In this calculation made by Valerio Boschi, it's clear that if we would evolve, for instance, the current tilt control base ring of the inverted pendulum into a 6 degrees of freedom active isolation stage, we would have several benefits. We would improve the residual RMS motion figures further compared to Virgo, which are already good, but they need to be better in the Einstein telescope. And we would have another practical impact on the detector design, because we could shorten the height of the towers without losing performance. That would have a positive impact on the infrastructure. So this is in terms of cost, for instance. So everything, of course, rely on the availability of suitable inertial sensors. In particular, again, this is an old story. We need tilt meters that are insensitive to linear acceleration. They are kind of the holy grail of seismic attenuation. So there is a lot of R&D already ongoing to develop advanced seismic sensors with much deeper, much better performance at the very low frequencies. Here I just took a few examples of what's happening now. Most of these devices that are both single axis or multi-axis, like the 6D interferometric readout inertial sensor being developed by Connor at the VU Amsterdam. They use optical readout or interferometric readout. So here you can see many examples. Also at Virgo, there is a lot of devices, that new device being tested next to the detector. Then, if you look at the panorama around Europe, there are new facilities where test bed for these new ideas or advanced ideas on seismic isolation are going to be tested. One example on the left side is the e-test facility in Liège. There we will have the chance to test seismic isolation platform in which we could combine active and passive isolation stages. This platform will be instrumented with advanced seismic sensors, so we could see how far we could go in terms of RMS motion with this advanced sensor compared to, for example, what's happening in LIGO. And we could try this hybrid approach that I was mentioning before, in which we mix up the best, I would say, of the two worlds. So the Virgo and CAGR experiences with ultra low frequency passive isolators and the active isolation system of LIGO. So that will be very interesting, and it would be a very important input for the design of the Einstein telescope isolators. Then I would like to mention also what will happen in the Pathfinder. In that case, we will stick to the standard passive isolation systems, like in Virgo and CAGR. But in this case, this happens mostly for practical reasons, but we will implement double inverted pendulum pre-isolation stage. So in this case, we will cascade to inverted pendula. This is an idea that was already proposed in the past. But in the Pathfinder will be really implemented for the first time. So it will be very interesting to see how it goes. So this for the seismic isolation part. Concerning the payload, again, we build on top of the Virgo experience. In this sketch is represented what more or less is a payload. So the payload is the mirror, of course, a reaction mass coaxial to the mirror, so that you can actuate from that to the mirror. And then there is the so-called marionette that allows large dynamic range, angular and longitudinal mirror control. So what is very important for the payload is the reduction of the Brownian noise of the last suspension stage. In the AT designs, we will certainly, so the aim is to improve the figures compared to current detectors, both for the room temperature, high frequency interferometers, and also for the low frequency ones. The main thing that we will do is to have longer final suspension stage, larger masses for the mirrors, and in the low frequency one, we'll also reduce the temperature. So what we do expect is to have, if you look at this graph, we expect a 6-fold improvement in displacement noise at room temperature, up to 50-fold improvement at low temperature for the low frequency detectors. For the payload development, there is a lot of R&D to be done. And here I would just enlighten two critical aspects that need to be addressed in short term, relatively short term. So the main one is so for the low frequency detector, the baseline design foresees silicon suspensions, monocrystalline. So the requirements are very aggressive. We need to combine ultra low mechanical losses. We want to have high thermal conductivity below 20 Kelvin. And this suspension should be reliable. So there should be kind of robust as well. The path is still very long. Now, in all test structures that have been tested, the low breaking stress is severely constrained the mechanical design. On that, we need to find ways to improve as much as possible the quality of the surface of the suspension fibers. This is the critical aspect. There are a lot of manufacturing methods that are under investigation. Making thin fibers very long that have all these properties is difficult. So micropooling has been tested or investigated. Etching from large crystal or wafers or laser heated pretzel growth methods or glass clad silicon methods. You will hear tomorrow this new technique. And then, of course, in realizing this suspension, a very important aspect would be to find a fabrication method that allow to have tapered ends at the fiber attachment points. It would be a major breakthrough because that would mean high suppression of clamping losses, much easier assembly, etc. But this is still ongoing. Is I would say almost at the beginning. I would just like to cite two of the R&D works that are ongoing at the moment. This is at Glasgow. They're just testing a short ribbon suspension to see how it works at low temperature, and then the group of Perugia, in collaboration with CAGRA, they are testing suspension structures, round suspension structure. They're measuring the thermal properties, breaking stress, etc. It's already nice to see that thermal conductivity figures in these thin fibers already in the prototype that are being made so far, they approach the bulk thermal conductivity of silicon. This is a good news, I think. So at least that aspect seems not to be too critical. Then another thing that we have to face for the low frequency detector is the interaction between the suspension and the cryogenic plant. We can profit enormously from the experience that has been done and is being done by CAGRA. In fact, the current ET baseline foresees a vibration isolated ET link as in CAGRA. But the low frequency requirements are much more stringent in the ETLF compared to CAGRA. So we need to work on it. So of course, on one side, we need to develop quiet cryocoolers, but we had also to improve our understanding of the ET link dynamics. So we need to model and validate these models to have a sensible impact on the design. Some studies just started. This is the one that is that will start soon for the ET Pathfinder. So we developed finite element models of ET links, and we managed to do simulations showing the residual transfer of vibration from all these ET links. And then we are now trying to validate the model. So this is what's happening at NICEF for the Pathfinder. So in terms of organization of the division, more or less, there is nothing special in the sense that the division is just reflects the typical structure of a seismic isolator and suspension system. What I would like to stress is that we decided in this case to have a common work package to design the payloads of the suspensions, both at high frequency and low frequency, because so many aspects are common, and in this work package 3, we would like to address all interfaces that the payload has. The payload need to have with the suspension chain and with the cryogenic plant and with the last stage mirror suspension. And we had defined a specific work package 4, for the material related aspects. So really the engineering design of both fused silica and crystalline silicon suspension elements for the because there are many things in common. There are bonding techniques to be defined and studied, and manufacturing method, etc. So everything that is related to the fabrication of the last stage suspension, we put everything in the same work package. So to conclude, we are now moving towards the TDR. We must treasure the experience that we have gained in 2G detectors and CAGRA to inform the ET suspension design. Here, I would like to stress again that there are R&D activities that are needed to inform the TDR. This is not non-exhaustive list. I just mentioned 2 major aspects that need to be addressed. So we have to improve the design of seismic isolation platforms, because this would have a lot of advantages. We will reduce RMS noise figures. We could shorten the length of the suspension chain, so we could have an impact on the infrastructure. And we need to learn how to make monocrystalline silicon suspension that are reliable and at the right size for the ET-LF design. In this sense, the amount of work is really huge. We need to put resources on this research line, and certainly we need to expand the capability of testing samples. So in this case, a coordinated effort between all labs that are interested in contributing on the same way how it's already happening for the coatings would be really desirable. Okay, and this was my last slide.
Thank you very much, Alessandro. Also for being in time. We have time for a few questions. Jeppo, please go ahead.
Hello, can you hear me?
Yes.
My comment is on this choice of using silicon for suspension. I wonder if we have to still continuing to think sapphire as a possible material. The reason why I think it's still a possibility is because at the moment there is not any lab in the world that is developing both substrate in silicon and suspension in silicon. Whereas for sapphire, there is already one laboratory that is doing this. So I wonder if, sometimes it would be much more important to have a scientific laboratory that is dedicated to develop the material, rather than to be based on the production of some enterprises. And for suspension, sapphire is much robust than silicon.
Yeah, I think silicon is now the baseline, but the sapphire is still not out of the game. This I agree. Yeah, so hybrid solution with silicon mirror and sapphire suspension are not out of the game, because as you said, as silicon suspension comparable to what they have in CAGRA is still far from being made. So we indeed.
Yeah, but and still, maybe this is a big question for all the projects. I mean, a lot of people are working on silicon as material for the substrate. But I repeat, there is no laboratory in the world that will take care of our needs for what regards the silicon substrate. So we should not do like our colleagues in the United States that are relying on the Shinetsu facility in California to produce, to develop the material that is good for us. I think this is really dangerous.
Thank you, Jeppo. This is actually a very important comment. We have time for one more quick question, Giovanni.
Yes, thank you, Alessandro, for the very nice presentation. I have a question on slide 8. I would like to know a bit more about these two R&Ds on the active platforms, namely what are the objectives, and if then some next steps is already foreseen in terms of integration of an active platform with a passive isolator SA-like. Yeah, just if you can tell me a bit more.
Yeah, so in this facility, that is, so this project just started. So the sketches that you see here are the two preliminary option for the construction of this test setup. So the idea in this setup is to look at two aspects. So the cryogenic one. So there is a cryostat with a kind of full-scale payload inside. You can see that, and then the idea is to also use this setup to investigate new design for the seismic isolation platforms. So the idea so far, is to have certainly at least one active isolation platform in the system, one stage, I would say. Then we are now internally discussing which one of the two we should pursue. There are limitations from the size of the vacuum chamber that is available there, so that is already a big help in terms of budget. But yeah, so my personal preference would be to go to the system on the right side, because that I mean that would be the synthesis, as I said, between active isolation and inverted pendulum systems with passive filters, etc. So Virgo-like. We could see how far we can go with that. At the moment, the status that are just rigid body simulations ongoing, with also including controls. The system is not designed yet. So there is at the moment, this will be in a single object, of course. There is no interferometer, nothing. So the only thing that we could be tested here is the integration aspects between the two worlds. And since this instrument will be instrumented with advanced inertial sensors, the only thing we could prove is that this seismic platform is capable of reaching the noise of these sensors, because we have no interferometer to go any further. But yeah, it's still being developed. So suggestions and inputs are very welcome, I think. I don't know if Christophe Colette is connected. Maybe he wants to add something to this.
May I propose that we go ahead with the presentation, and maybe we can come back again on this point in the discussion at the end of the session.
Yes.
Thank you. Thank you very much. So Alessandro, can you stop your sharing? Thank you. Next talk is about the optics division. I see Stuart ready to start. We see your slides. Please, Stuart, you can start whenever you want.
Okay, thank you. Just let me know if you can't hear me.
Very well.
Carry on. So yeah, within the optics division, Edwidge and myself will both present. So I'll start off and pass over to her. So the optics division contains a number of systems within the Einstein telescope. So we're looking at the core optics, laser sources, input and output optics, squeezed light sources, wavefront sensing and control, and scattered light. And we have, I won't go through in much detail because we've already had kind of an overview of these in several of the previous talks in this meeting, but we have ETLF, very stringent requirements for low optical loss, low mechanical loss, and low noise. And then ETHF, where we have the added challenge of very high power, very high optical powers within the Fabry-Perot cavities. If we have a look at the boundary conditions that we're operating to, or we're expecting to operate within, for ETHF, we have 3 megawatts circulating power within the optical cavities at 1064, expected to use 12 centimeter beam radius radii on the mirrors, and this will be at room temperature. Substrates, as has already been discussed, fused silica at 200 kilograms for the test masses. This is 5 times that of advanced LIGO and advanced Virgo, but interestingly, it's only 2 times what Virgo Plus are proposing to use, and those substrates are already manufactured, as far as I'm aware, from Jérôme's update to me last night, and these should be shipped to LMA at the end of this year, which is more or less now. And there's other companies, just following on the discussion about the availability of large substrates. For fused silica, we have 3 suppliers who are all trying to develop very large ultra pure silica ingots. And so we also have Corning, Heraeus, which is a current supplier for many of our current detectors. And this is a picture from Nikon, who grew, this is the largest silica ingot that they've grown. So for substrates, certainly looks like there's the technology is there to fabricate very large silica substrates. Coatings, we require 4 times reduction in the coating mechanical loss compared to the current advanced LIGO, advanced Virgo coatings. This isn't really a precise number, because we also need to take into account the optical properties. So if we're using coatings of the same optical properties in terms of refractive index, then this is true, but of course it will change if we change to other materials. But broadly speaking, we're looking at a 4 times reduction. Thermal compensation system is probably going to limit the permittable absorption in the coatings to around 0.5 parts per million, and scatter has been set within the design to be 10 to 20 parts per million. But again, one of the motivations at this stage within Einstein Telescope Consortium is the system integration and how we link all the components together. And the fact that scatter has been a major challenge for the second generation detectors, clearly we're going to have to look into this in detail. The availability of coatings over large substrates of around 62 centimeter diameter are not really available at the moment, but there are plans in a number of labs. This is the system that's currently being procured in the UK from Cutting Edge Coatings in Germany, able to coat 2 620 millimeter diameter optics at the same time, and the similar work in LMA to create the facilities for coating these large area optics. Within the low frequency part of the Einstein telescope, we then operate at cryogenic temperature with much lower circulating laser power. So we're now down to 18 kilowatts instead of 3 megawatts. But we push the wavelength out to 1550 nanometers, which opens up the possibility of using silicon substrates for the test masses. Again, 12 centimeter beam radii and 10 Kelvin operation. But again, when we think about system integration, we need to check whether this temperature is achievable when we take into account the other cryogenic and suspension performances. The substrates, we expect to use 211 kilogram single crystal silicon, but as was highlighted in the previous discussions, there's not currently a supplier of this size of silicon ingot, and there's no supplier for ingots that have greater diameter than 450 millimeters. And so we are either reliant on industry developing this or setting up a lab ourselves. But there's a lot of work within industry trying to push the optical properties of these very large silicon ingots. But of course, sapphire is still on the table as a consideration. There's also a lot of modeling that's being done for how these cryogenic suspensions will operate. So I just cite one of those there, but many groups are working on that. That's in terms of the substrates and test masses, but in terms of the coatings, again, if we consider the same optical properties, then we require a 3.8 times reduction in the coating mechanical loss compared to current coatings at 10 Kelvin. Absorption, we expect to be set at 5 ppm or less, but that will, again, be informed, the exact number or permittable absorption will be informed by the cryogenic and suspensions work that's being done. I just want to cite a couple of very important updates recently from within our community that informs where we might be going, in particular with the coatings. This work by Kiran Prasai in Stanford was looking at atomic simulations Here are some grazing instance pair distribution function studies where the atomic structure was analyzed. There were some particular features within the Tantala coatings that they were looking at in relation to face shearing atomic structure, edge shearing, and corner shearing. When we looked at how these atomic structures varied with annealing, now typically when we increase the annealing temperature, we decrease the mechanical loss, and we saw that face shearing structures decreased, as did edge shearing, but corner shearing increased. And so there was an implication here that, in fact, for room temperature coatings, we really want, if we're using oxides, we want atomic structures which are preferring this corner shearing atomic network. And then if you look at other papers, this is an example plot from Kieran Craig's paper last year as well. We can see that certain materials like fused silica, which we know as a coating material, I haven't drawn the plot there, but 300 Kelvin, this comes down to at least 5 times 10 to the minus 5, so very low mechanical loss. And so as a room temperature material, silica looks really attractive, but as we go to cryogenic temperatures, we can see that actually this is a high loss material. And then we look at other materials like this is silica hafnia alloy. Low temperature, this looks quite nice, but as we go up towards room temperature, it then becomes the highest dissipation material of the ones studied here. And so there's this effect where we look at the corner shearing polyhedral structure within the materials. If we link the materials studied in these two papers in order, we've got silica hafnia, then tantala, then silica. And the cryogenic loss follows this. So silica hafnia has the lowest mechanical loss. We can see that here. And silica is the highest. But when we look at the room temperature mechanical losses, we get the exact opposite trend. And so this is very informative for our studies within the Einstein telescope, because this suggests that if we were using amorphous oxide materials, we're very likely going to be choosing different materials for the high frequency and low frequency components because of these opposing effects with the mechanical loss. There's lots of work being done in other groups in terms of kind of the atomic simulation studies. I just cite one by Poissy, looking at applying a stress within the atomic structure, computing a strain, and quantifying the phase shift. And that's known, then found to be correlated to the measured mechanical losses. And there's some really nice results trying to tie in the low temperature dissipation peak in Tantala coatings in relation to these simulations. And this is the paper again by Kieran Craig, which actually produces a possible coating solution for ET-LF, and that uses a mixed material coating design where we bury amorphous silicon containing multi-layer mirror coatings in the under layers where the electric field intensity is low, but in the upper layers where we have a high amount of the laser light reflected, we switch to materials which have very high optical properties. And that allows us to mix materials which have good mechanical properties and good optical properties and appropriately position them in the coating so that we can exploit both the optical performance and the low mechanical losses. There are other materials which are being considered. I just cite some work being done across Europe and within the LSC on silicon nitride, which looks like an attractive mirror coating. We also have, when we look beyond amorphous coatings, this crystalline coating. So aluminium gallium arsenide is one which is often discussed as being a really attractive technology, but it requires a substrate transfer from the gallium arsenide wafers that these coatings are epitaxially grown from, which could cause some challenges when we consider the level of scale up we require for ET. There's other crystalline technologies that could be lattice matched to the test masses. So aluminium gallium phosphide would be an example of a crystalline mirror solution that could be lattice matched to crystalline silicon. Amorphous silicon is still a really attractive material, but at the moment can't be considered as the only high index material in a multi-layer structure because the absorption is too high. And there's other materials. Gallium nitride looks very promising, but it's underexplored. But within both the Virgo and the LIGO collaborations, this material is on our to-do list. And there's the various oxides that the atomic simulation work has been proposing could be attractive for ETHF, such as titania germania, which is currently the most likely material, high index material for A+ and perhaps for V+. And there's other oxides such as tellurium, which look attractive in terms of this corner shearing network. I'm going to pass over to Edwidge now and mute my microphone.
Thank you, Stuart. Good afternoon, everybody. So I'm going to go on with the remaining work packages, starting with the laser source, which is the first, the input beam, which gives the input beam to the interferometer. I'm going to go through the requirements for this laser source, which is quite different if we talk about the HF ET or the LF low frequency ET. So for the high frequency, we want to push the shot noise down a very low level. So that's why we need very high power, around 700 watts. Which means that we will have a high thermal effects in the ITF. The laser source needs to deliver good beam quality, low beam pointing noise, and low intensity noise, and the actual requirement would be around a factor 10 below the Advanced Virgo Plus requirement. So that's a big challenge that we will have to face. You also need low phase noise. All these noises will impact the sensitivity. Of course, you need also a highly reliable laser system, as this is a key to a good duty cycle. For the low frequency ET, the power is much lower. But the challenge here is to reach very low noise at low frequency, as we already heard Alessandro discussing about this. And in our optics division, the challenge here will be to reach this, to limit the technical noises, not to pollute the low frequency sensitivity, so which means very low beam jitter and very low scattered light, because these are typical noises which can impact the low frequency. So this will be another very big challenge. The present technology that is used in the Advanced Virgo Plus, for example, is a fiber amplifier aiming about 100 watts. So we could still base ET on this technology, for pushing further the power and combining coherently several sources to reach the 700 watts. So after the laser, you have the first stage of filtering, which was the pre-mode cleaner. And after that, you have all the input optics, which give further filtering of the beam. So this is the interface between the laser and the interferometer. Most of the components are located under vacuum. So it further filters the beam in order to give a pure TM00 to the ATF. It gives further filtering and stabilization in frequency, power, and beam pointing. And it also provides a phase modulation, creating sidebands to the beam, which is used for longitudinal and angular control. The main components of this system are electro-optic modulators for the phase modulation, Faraday isolator, and mode cleaner cavities. So both the electro-optic modulator and Faraday isolator can undergo very high thermal effects, because they will be this crystal will be traversed by high power. So this is one of the challenge in the development of those components. Faraday isolator also needs to be highly vacuum compatible. So we can base on the technology which is already existing in the present interferometer for ETHF, but for the ETLF, we need to develop this technology for the given wavelengths. The mode cleaner cavity can be based also on the existing technology, but improving, because we will face higher radiation pressure.
5 minutes, Edwige.
Okay, thank you. And thermal effects as well. So next slide. At the other end of the interferometer, you find the output optics. the role of the output optic system is the main role is to read out the dark fringe beam carrying the gravitational wave signal, but also to read out all the auxiliary beams which are, for example, at the end station of the interferometer and which are used for the controls. So it mainly provides the mold filtering of the dark fringe to remove all the high order modes which can be created by the defects of the core optics, for example. It also allows injection of the squeezed light and at the end the photo detection of the beam. So the main components are mode matching telescope to match the beam from the ITF to the output mode cleaner, for example. Faraday isolator, output mode cleaner, and photodiode. So the key thing here is to have very low optical loss, because each fraction of the light that you lose is a reduction of your sensitivity. So Faraday isolator should have low absorption, output mode cleaner as well. So the current technology for the output mode cleaner is two different technologies. A monolithic cavity as used in Virgo, from which you see the picture here, or the so-called tombstone cavity, which is used in the GEO or LIGO. Both have pros and cons, and we will have to evaluate which technology can be the best for ET. So entering from the output optic side, we will inject squeezed light, which will, so this system is providing the squeezed light at the required angle. So the aim is to have, of course, a frequency dependent squeezed light. It's composed of several systems. There is a squeezed light source, which is this complicated optical setup that you see at the bottom right. Faraday isolator again, and the filter cavity, which are crucial to orientate the ellipse of the squeezed light at the proper angle and at a frequency dependent value. It's also very critical here to have very low optical losses, especially if we want to reach a very high squeezing level, and also very low phase noise for the filter cavities. So here again, we can base the technology on what's existing and what's being tested in the advanced detectors. So frequency dependent independent squeezing has already been proved to work in the advanced Virgo Plus and advanced LIGO Plus at 2 to 3 dB. But we need to push further and reduce the losses, and the frequency dependent squeezing will be tested in advanced Virgo Plus and advanced LIGO Plus, and it will give crucial inputs to the ET technology. Of course, all this is at 1 micron wavelength, and it needs to be completely developed at 1.5 micron for ETA LF. Another subsystem of the optics division is the wavefront sensing and control. So this is very challenging for the ETHF, where we will have large thermal effects with very large power circulating into the Fabry-Perot cavities. So it will induce deformation of the optics, which we will have to correct in order to have the best matching between the ITF cavities and the input beam. So this requires sensing the core optics deformation for global thermal effect, but also for point absorbers, and then correct for this deformation. It will also have to face the thermal transient during the lock acquisition of the ITF. So typical components are wavefront sensors, sensing the deformation of each of the core optics, and then ring heaters or CO2 laser for collecting. So that's what is actually used in the advanced detectors, but probably we can think about other tools for this wavefront sensing and control system. And finally, last but not least, we have a system for the scattered light mitigation. So you already heard about that. As you know, we take a lot of care in designing all the optics to have as less scattered light as possible, but there is always a little bit of light which is scattered by all the components that the light is passing through. And this light can bounce on the surrounding materials and be recombined again with the interferometer main beam, bringing the phase noise that is induced by the motion of the scattering object. And a little bit of scattered light can induce a very large noise in the ITF. So we need really to tackle all these problems from different fronts. First is modeling of scattered light, how it is generated and how it couples to the ITF. And the second point is the reduction of all this scattered light by the optical elements. So the key components are first to provide simulation software to be able to understand what are the crucial points in the ITF optical design that we need to be very careful and understand the coupling, give guidelines for the design of the optical bunches, and also develop a monitoring system for monitoring the scattered light, like, for example, is done in the Advanced Virgo Plus with the instrumented baffle. Of course, reduce the amount of scattered light with high quality baffles, beam dumps, also good design of the photodiodes, which are known to scatter a lot. And also reduction of the mechanical resonances, which show up through the scattering elements in the noise of the interferometer. So to conclude, I hope that we have shown you that there are many challenges ahead of us. Just here, very few are listed here. I'm sure we forgot a lot, and a lot will show up when we actually really dig into the design. But for HF, for example, we need a high power laser. We need to reduce and control the thermal effects, minimize all the optical and mechanical losses, and lower all the noise that can spoil the sensitivity, like scattered light, very good photodetectors, and so on. And for the low frequency, we need to develop a lot of technology here, like, for example, the squid lights, Faraday isolator, and also actually understand what needs to be done to reach the very good sensitivity at low frequency, so reducing beam jitter and scattered light, and also minimize here the optical and mechanical losses as for the ETHF. So do not hesitate to join us for this big effort, and please contact us if you want to participate. And I want to highlight also the two related R&D talks that you will have tomorrow in the ISB session of tomorrow by Walid and Jessica. That's all. Thank you.
Thank you. Thank you both. We are running a few minutes late, but let's have one quick question. I don't see any hands raised, no comments in the chat. So if there are no questions, let's move forward. Next talk is about the active noise mitigation division, and Connor is ready to start. Please go ahead.
Hi, thank you, Gianluca. Can I be seen and heard okay?
Very well, thank you.
All right, so active noise mitigation is Division 5 of the ISB, and it's co-chaired by myself and Jan Harms. And it's really focused on trying to avoid making design decisions, particularly at the early stage, where we're going to run into intractable problems later. It's also about acknowledging the reality that achieving low frequency noise in ET, especially ET-LF, will be extremely demanding. So we'll have a first look at the outline of the division, and after that I'm going to talk about two example cases. Well, I'll talk about one and Jan will talk about the second one towards the end of the talk, and we'll only touch a little bit on the remaining work packages. So there are a lot of known issues that affect the performance of current and future detectors, especially at low frequencies. Some of these are really only known inside the control rooms of the detectors by expert commissioners, and many of them are known outside. What we really need to do at the moment is work to address these largest known issues by design and with realistic inputs from the current LBK advanced and A+ instruments. And we can't be too optimistic about the low frequencies. And I feel this is where we're going to really draw most on the actual commissioning experiences of people. So our divisions at the moment, just to run through them, we have Newtonian noise, environmental sensors, magnetic noise, inter-platform motion, and low frequency noise. I won't go into detail about what each of these things are. I'm going to focus myself on low frequency control noise, and I'll give a pointer to a talk tomorrow about inter-platform motion, and Jan will address the first 3 points, at least at some level of detail at the end of this talk. So this is a curve I think we're all used to seeing. We talk about the Einstein telescope being roughly a factor of 10 better than current instruments, and we see that across much of the range from, say, 30 or 40 hertz up. And what I want to do is zoom in on the range that active noise mitigation is focusing on. So we're going to cut this off at 100 hertz and look down. And what we see is kind of interesting. If we actually put this in terms of displacement, you know, when we look over this very friendly frequency around 50 hertz, we actually only need a factor of 5 over LIGO 03 in displacement. But already at 10 hertz, we see we need to be not 10 times better than Virgo, but 1,000 times better than Virgo at 10 hertz. But when we hear other talks, we talk about not only do we go down by a factor of 10, we go a little bit to the left. And I think it's easy to say a little bit to the left, but another thing entirely to say how many orders of magnitude do we have to go down in order to go left by a factor of 3. So the number we quote in the updated conceptual design report, the updated design study, is 3 hertz. And it's not a fair comparison because the commissioners are not trying to optimize the noise of the instruments at 3 hertz, but they're for sure not trying to make it worse at these frequencies. And we see that depending on the control loops and the different requirements of the sites, we need somewhere between, you know, 250,000 and several million reduction in noise at 3 hertz. So we'll round it off and say that ET is not 10 times better than second gen. It's 1,000,000 times better at 3 hertz. And if we're serious about this goal of getting astrophysical sensitivity at this region, we have to systematically identify and mitigate low frequency noise by addressing at least the killer things we know. Alessandro already mentioned RMS motion, and I think this is my favorite one to talk about. We know that a lot of couplings, and I'll touch on this a bit later, come through the fact that we have to suppress the angular motion to below some level driven by optical requirements, and that those sensors and actuators couple into DARM. We know that we have actuation forces, and particularly 20 hertz and below, we know that coil drivers can limit the sensitivity. There's angle to length couplings, length to angle to couplings, angle to length to angle. There's a whole forest, and there's many more. So this is what I'm talking about when I say low frequency controls noise, is all of the things that are not DARM controls that get into DARM. This is one of my favorite examples, and I like it because I think it's somewhat understood by people who work in commissioning, but from offsite, this is not at all clear. So this came out of the workshop that we held at the University of Birmingham with both Virgo and LIGO people in 2018. There was a summary talk given at the Maastricht LBC. We know that angular control noise is a limiting noise source, and we know that it gets into our gravitational wave channel through coupling mechanisms in the suspension from length to angle and back again. And in the case of LIGO, we just draw the suspension chain to show that we couple pitch to length, pitch, and so on. We have length drive because the isolation tables in LIGO or filter 0 in Virgo aren't perfectly quiet. And the reason they're not perfectly quiet is at least due in part to the tilt-to-translation coupling in seismometers. I like this example because it's complicated. It spans several divisions of the ET instrument science board and many areas of the current detectors. And it's actually a bridge, a direct bridge from an effect we normally only consider at 10 millihertz way into the gravitational wave band. Now, this is a slide here from enhanced LIGO, so you see the alignment noise coming all the way up to something like 30 hertz. And we know that it's not really limiting at these frequencies in the current detectors, but when we go down towards 20 hertz, 15 hertz, we know that this is a big problem. So this is a graphic that I made to try and identify some of the different regions and to sort of broadly say, what do we mean when we talk about RMS reduction? How much do we need to improve by and where? It's already been presented in several of the talks today, so I feel like I did a good job at least making it look nice. So we talk about tilt coupling and earthquakes at very low frequency, where earthquakes are really driving the modes of the planet at very low frequencies. Tilt coupling, we talk about this where our factor of G over omega squared becomes very important at low frequencies. We heard Alessandro talking about the microseismic peak being the major drive of low frequency RMS or ground RMS motion. We have what we consider the normal mode resonances where we know we need the motion to be very low. And then we have the gravitational band here on up. And we need to develop different technologies to address different parts in this band. So we've heard time and again that we need tilt meters to improve our low frequencies. But the advent of tilt meters and active tilt control lets us use our inertial sensors better at the microseismic peaks. So we get this kind of flow-on effect from one technology stage into the next. But one thing that I would like to point out is that we see this slope in both the LIGO and the Virgo spectra, and this slope is not the attenuation you expect from a super attenuator or a LIGO quadruple. It's significantly shallower than that. We know that there's some kind of noise that's coming with this 1 over f to the 5th or 1 over f to the 4th kind of slope. So it seems a bit unrealistic to expect that we can get a much steeper slope when we go to the Einstein telescope. And so we're going to find that if we want sensitivity at 3 hertz, we're going to have a realistic expectation of the nonlinear upconversion of the couplings, of the cross couplings at frequencies below that. So the solution spans several divisions, and I see the role of active noise mitigation as being to bring attention where it's needed for R&D work, to highlight the links between the divisions, and to focus effort where we think the biggest and scariest problems are. This is, of course, a little bit uncomfortable to look at the hardest parts of the spectrum and focus time and effort there, but we have to do this already before we build ourselves a design that might not be able to reach our 3 hertz targets. So that's dynamic range and input motion we've already heard about. Zina will talk tomorrow about inter-platform motion, where we stop talking about inertial motion of the test mass and we start talking about the relative motion of not just the core optics to each other, but the core optics to everything that they communicate with. That includes the detection benches and telescopes, beam diverters. We need to reduce the auxiliary couplings, and this can be by either motion or by reducing the coupling factors, but it needs to be done in a realistic fashion. And we need to do it with an eye on what the actual controls will be as they're implemented. And for all of these things, we need to have more consistent models for converting input motion via auxiliary controllers into the gravitational wave channel. So if I phrase this differently, we need to have a better understanding for how the requirement for h of t at 3 hertz flows into each system and subsystem. Now, these are things that aren't new in our field, and there was a very nice talk given by Brian Lantz at the latest LVK meeting, where he talks about getting bigger than what we would have called a system before, which is a ham ISI in this case, plus a small suspension and some tip tilts for beam steering. And considering this as being a system, and in this case, he's only talking about the corner station, but now he's brought in angular degrees of freedom, relative motion between points. This is also not new. In Virgo, there's the microseism free control and the offloading of LSC signals, and these are all crucial parts of it. So we need to be looking at these effects with a very serious eye towards the RMS motion, where these signals go, how this control hierarchy is built up. So at this point, I'd like to give a shout out for Zina, who's been working on suspension platform interferometers at the AEI and on inertial sensors. She'll talk tomorrow at 3:20, and this is an example of one of her slides talking about the difficulties making sure that we allow ourselves enough room for diagnostics for stabilizing at what we now call the seismic platform level.
We have 5 minutes, Connor.
Right, so then I have to hand over to Jan, who has to deal with the 5 minutes, and I'll mute my microphone.
All right, can you hear me?
Yes.
Okay, perfect. So just a couple of slides I want to add. So first, Newtonian noise. We have heard about this a couple of times during the symposium already, but why is it in active noise mitigation? So the thing is that in the initial conceptual design study, the plan was, okay, how low can we go in frequency when we are underground without really running into trouble with Newtonian noise? And some estimates were made. I mean, and later on, these were refined. And what we saw is that, in fact, the targets, the sensitivity targets that we set ourselves probably cannot, well, not necessarily at least, be achieved without further mitigation of Newtonian noise. And so there are many contributions, but in the end, when it comes to further mitigation, we are just worried about two, essentially. And this is acoustic Newtonian noise, so the sound field in the air, in the atmosphere producing gravity fluctuations, and the seismic Newtonian noise. So for the acoustic Newtonian noise, the story is simple. Whatever, when you are even just 100 meters underground, then whatever happens above surface in the atmosphere, unless it's a very loud place, and you have to be careful, we were thinking about this a little bit, if you have, for example, a wind park, you might have significant perturbations in the sound field, even at the surface, that might enhance the noise. But let's say if you are in a, not such a difficult place, then already being 100 meters underground is enough to get rid essentially of this atmospheric acoustic Newtonian noise. But this is not the complete part, because even the air volume inside the caverns that host the test masses will have their sound field. We know that this can probably also be quite noisy down there. At least the impression that you also get when you are, for example, underground visiting the cargo detector. So for that reason, you should be prepared that the noise from the caverns might be important, and that you want to do some cancellation of that noise. I will talk about this exactly how that would work. But the same story for the seismic Newtonian noise. So we heard already, if you go underground, then you can strongly attenuate, reduce the surface Newtonian noise from surface waves. And that depends very much on geology. The range of values that you see here in the plot are actually not even reflecting the complete conceivable range of suppression, because it really very much depends on geology. This is just like to give some idea. What you cannot get rid of is the body wave contribution, and that depends then on your site quality, how much you have to do against it. Okay, so, Connor, you are the one in control, I forgot. Okay, something that we also have to keep in mind is that we always look at the natural background of these fields, but then the infrastructure can also create noise. We know this, for example, from all the sites actually, but just to give you an example from LIGO Hanford, where they did the following, they had like a power outage and all the machines like ventilation, chillers, pumps were off for some time. And they measured the ground spectrum, the seismic ground spectrum. Now, if you compare this with the spectrum when all these machines are on, then you can see that it is significantly above that level, maybe almost a factor 10. So what you can see is that at least, for what we call the Newtonian noise band in the current detectors, which is between 10 and 20 hertz, that all the ground motion is really dominated by the sources that you have at the site, part of the infrastructure. So, and we, of course, want to avoid this to happen for ET very much, because we want to pay a lot of money profiting going underground, and so we do not want to spoil that advantage. So, if you look at Kagra, for example, then you can see that the seismic spectrum actually is still very, very low and close to the minimum that you can expect for any site, even though they have the infrastructure already in place with, also for sure a ventilation system, pumps, and so on and so forth. They have these cryogenic systems. So that means you can achieve underground a very low noise environment, even with the infrastructure in place. So that should encourage us. What is not shown is that there's a lot of excess noise above 20 hertz, at the Cabra site, which you might try to avoid at ET, but which is not really a major issue at least when it comes to Newtonian noise. Okay, next slide. So just very briefly to explain cancellation, I think most of you are familiar with that idea. You would deploy seismometers, for example, or environmental sensors around the test masses, and then you use all of the data from these sensors as input to going to an input of a linear filter. And that output of that linear filter is an estimate of the gravity fluctuations associated with, for example, in this case, the seismic field. So this is something that we are currently developing at for Virgo. And you can see that we have sensors deployed in the end buildings, also now at the central building, and we are currently learning how to use their data. So this is in progress and should be ready for the next science run. Okay, next slide. So now something that is related to Newtonian noise, but not only, is that we have to work on our environmental sensing. And there are various problems associated with that. This is, for example, you can, of course, try to increase environmental sensitivity of environmental sensors. This is, of course, work in progress as part of the systems that we already heard about today, but also interesting to environmental sensing because we need these also for noise cancellation. Then, for example, to pick another prominent problem is for the acoustic sensors. If you want to do monitoring of acoustic fields in the atmosphere, which is something that we currently do not consider, but which might be interesting if for some reason we consider depth to be shallower than 200 meters for ET, then this is a problem to solve, essentially to protect the microphones that are deployed at the surface from wind, influence of wind, which is the main reason why we cannot really do Newtonian noise cancellation of atmospheric acoustic Newtonian noise. The wind turbulences produce pressure fluctuations locally around microphones, which makes them essentially useless for cancellation of acoustic Newtonian noise. So that is something that you can address with windshields, which are also being developed. Then, of course, distributed arrays of sensors. How do you make it easy to deploy them, to operate them, and so on and so forth? So that is sorry, I'm a bit perturbed here. This is a big problem to solve, especially if you think about seismic sensors, which have to be deployed in boreholes, which will be a very expensive and complex system to operate if needed. And of course, there's a lot going on in this direction. Okay, next slide, please. So the last thing I want to say is that the issue that we do not often talk about is magnetic noise. And this is being investigated also for the current detectors, and noise projections tell you that at the moment we are not really strongly worried about magnetic noise. It lies comfortably at most frequencies below the current instrument noise. But okay, there are maybe some isolated frequency bands where it already becomes kind of important. But if you look at the noise that you have, it is going. If that is, if the magnetic spectra that we will have around the test masses at ET are similar to the magnetic spectra that we have today, and if the coupling to the detector is similar to what we observe today in LIGO and Virgo, then we would be limited by magnetic noise by orders of magnitude at low frequency. So this is another thing that we really have to take care of. It is kind of a more tractable problem compared to, for example, Newtonian noise, because you can address it already by design of, for example, payload and other specific components. But nonetheless, I think we have not really spent much time on addressing that problem in the instrument design yet. But of course, we can draw from a lot of experience from the commissioning teams that are working on this. And that will be an important thing. Magnetic noise, for sure, is something, it's not only a direct sensitivity limitation. As you might know, these can also be at these very low frequencies, correlated fluctuations between largely separated points around the globe because of the Schumann resonances. And this can lead, even if it's a subdominant contribution, below other instrument noise, it can lead to subsequent limitations, for example, of searches of the stochastic gravitational wave background that use correlations between different detectors. And so this is something that makes this a little bit, quite important to be sure that the noise is not just limiting, but really well below essentially the instrument noise to not later be a kind of problem for these stochastic searches. And yes, so at this point, I want to stop. Thanks.
Thank you. Thank you both, Connor and Ian. I see one question in the chat. Irene, do you want to?
Yes. Hello. Yeah, it's as Jan raised the point of the importance of having a quiet infrastructure. So I wonder if this is considered as a task of this division. Let's say the good design rules, putting requirements and good practice and so on for the design of a low noise infrastructure is going to be part of this division, or is considered somewhere else?
So I think it will be a collaboration between different parts of the organization. So for sure, our division has to give inputs like what is the acceptable noise level for ET. But then the infrastructure division, of course, is the one that has to really put the, to make the plans for the infrastructure according to the requirements that we can give. But I think formally, at the moment, there's also the site preparation board that is involved in this kind of discussion. So I think in the end, it will be all three components that will contribute to a solution, starting with the requirements from our division.
Yeah, can I make a quick comment on that? We actually had foreseen originally a specific work package on this in the infrastructure division, but after many discussions, that has been removed because we think that is really a prime example for something that cannot fit in one division exactly. So we need to make sure that this is not forgotten. I think even though the site preparation board will contribute, I think it's primarily the responsibility of this division to lead this intellectually, and the infrastructure division to provide expertise from outside of our field. That's how we have foreseen it at the moment. What I don't really like is that the name has dropped from the work packages, so we must make sure that we don't forget it.
Okay.
Can I ask a question, Gianluca?
Sure, go ahead.
Connor was talking about this factor of 1,000 that we are away at low frequency at 10 hertz from what Virgo in principle should be possible to do. Would it make sense to take some of these new ideas and new techniques that people are thinking about and to see how we could make this happen at Virgo?
If you're asking me, I think absolutely. And we see some parts of these technologies already implemented on site. There's tilt meters now both at LIGO and Virgo, and they've made some significant difference at LIGO. There's certainly investigations going on in LIGO for implementing some strategies from Virgo. So one of my students looked at employing something equivalent to the microseism-free control in the LIGO platform. Sorry. But in general, yes, any development in particularly inertial sensing for rotation could in principle be implemented on site at either Virgo or LIGO. And I think it's crucial that we do test those technologies on a large scale.
I think it would give quite some credibility to all these this push towards low frequency.
Yeah, that's right. I mean, you can't talk about a factor of 1,000,000 without some indication it's plausible.
Yeah. That's a sensible comment. So it's time for a break. We are a bit late, so my proposal is let's stop for 17 minutes and reconvene at 4:30. So see you in 15 minutes. Thank you.
Yeah, okay, thank you.